All right, guys, so I got a question from 3-4, number, which one?
14.
14. Says, comparing test scores on the SAT, this one, right, the SAT, have a mean of 1518. And a standard deviation of 325. Scores in the ACT have a mean of 21.1. And standard deviation of, where'd it go? 4.8. And it says which one is relatively better? An SAT of 1190 or an ACT of 16? Which is relatively better? Now this is a really blatant example of, you can't say, well, dude, man, I scored 1190, you scored 16, you suck. That's not fair because the whole scale is different. So it's kind of more subtle when I say, well, I scored a 72 in my history class and you made a 48 in your math class. I did better than you. But maybe the average in the math class was 46. Right? That's happened in the past. So that's a little more subtle though, because at least they're 0 to 100. So it's kind of like really easy to make that mistake. Here, that you can't really make that. Nobody's going to say, man, you only made a 16. You suck. No, it's not. That's not the same scale, right? These are down in the 20s. These are up in the thousands. So how do you tell which one's relatively better? What do you use? What shows relative position?
Use the standard.
Z-score. Use the standard deviation as the tick marks on a ruler. And the Z-score is where you actually take a measurement. So I want to measure how far this is away from its mean. And how far is this away from its mean. And then I can tell they're both below the mean, right? Obviously, if this guy scored a 22, and this guy scored an 1190, then this guy's better, because it would be above the mean. They're both below the mean. Whoever's least below the mean is better. So how do you set up the Z-score, for example, for the SAT?
1190 minus 15.
Yeah, my data point minus the mean divided by the standard deviation. See how many of these fit in there. How many steps are there between these two things? Cool. And you get whatever the hell you get. What do you get? Did you do it?
Negative 1.01.
1.01?
Yeah.
Now do the same thing for the SAT. I mean, for the ACT. If the ACT came out to be negative 1.5, then that's the worst score. It's further below the mean. If it comes out to be negative 0.9, the ACT is the better score. It's closer. It's not as far below the mean. They're both below average, but now you're just saying which one's more below average relative to its own scale, relative to everybody else's score. Is that all right? So again, that's number
14.
What was that? 14?
Yeah.
3, 4, number 14. Yeah.
28.
Same section, right?
Yeah.
That's all right. You can ask the question. Let's see. Listed below and range. Oh, okay. So this is a very small sample of data. What's the 5-number summary again? Of course, if you weren't here last time, you only 5 numbers.
25, 50, 75.
Yeah. So the low, the high, yeah, the Q1, the Q2, Q3. And then when you plot them out, you could do, this will be the low, Q1, Q2, Q3, high. That's how you make a box and whisker, right? I like my Q. Q1. That's how you do a box and whisker. Make sure the scale is consistent, or else all your box and whiskers will look the same, which is a little misleading. You can say, oh, all of the distributions in the world are the same. Freaky. No, it's not good. So your scale has to be consistent. So in this question, they ask you to take the data they give you, very small set of data, which kind of sucks. But you still go through the process. How would you find Q1, considering that in this case, how many data points are there?
10.
10? How would you find Q1? What's the first step to find Q1? What's Q1 mean? Yeah, 25% of the way in. So I want to go 25% of what?
Of 10.
Of 10. I want to go that far into the list. I want to go a quarter of the way into the list. What is 25% of 10? 2.5. What do I do with that number? Who remembers? If you
Rise up to
exactly. If it's a decimal, I don't care what it is, you take it up to the next whole number. If it's a whole number, you take that number and the next and average them. And that's really what we do with median. Average them, take the one and it's the same thing we do with the median, because the median is a case of, it is this. It's Q2. That's the median. So 2.5 tells me to go up to the third number. And the third number is, are they in order? Yeah, cool. 39. So there's a gimme. Keep going. You make Q2 the same way. You got to go 50% of the way in. 50% of 10 is 5, so you take the fifth and the sixth and you average them together. Okay, cool. So like I told you in the first day, statistics is concept heavy, math light, actually. The formulas are going to look kind of disgusting, but it's not very intensive math. The real difficulty in statistics is when do I do what formula do I use, what goes where, those kind of things. The math itself is not intensive. This is not intensive math at all. Yeah?
When we make those box and whisker plots, is it okay if we make like the low value and the high value the ends of our scale? Or do
As
you
long
want
as
to
you
go-
can fit the scale accordingly.
I mean, you can still have a high and a low and still have a scale, but is it okay?
As long as you can fit the scale in there. So if you have a scale of 5, it better naturally end on the highest one. Don't try to squeeze it in if it's going to be difficult though, you know? Especially if your high is 88.1. I don't want to be doing some weird ass 7.2 scale. Make your scale 5, 10, something nice to work with. Okay. Is that good?
Yeah,
Who
I
has
got it.
You got it? Okay. Number 2. Oh, I like this question. All right. From a conceptual standpoint, I just like that phrase. From a conceptual standpoint, Z-score measures what? The number of standard deviations. So if it has any units at all, the units is standard deviations, right? Officially, it doesn't have any units. And you can see that mathematically. If the mean height, does it give me anything here? No. I don't know centimeters. The normal mean height. I could have, let me think, 1 point something meters. So let's say 107 centimeters. Why not? And the standard deviation is 12 centimeters. That sounds great. What if there was a president that was 115 centimeters tall? What would his Z-score be? How would you calculate his Z-score?
115 minus 107.
So 115 minus 107, 115 centimeters minus 107 centimeters. You don't have to put the units in, but I'm just trying to make a point here. Divided by 12 centimeters, you get 8 centimeters over 12 centimeters. What do the centimeters do? Cancel. No units, right? Anybody had ever taken chemistry, you remember unit analysis? You see what the hell units are alive? None. No units are alive at the end. They all cancel. So Z-scores officially have no units. You could also look at it as having standard deviation as units, but officially there's no units. Cool. All right. And that's why I can compare them to other things that might not have the same. If I'm saying my town is 5 kilometers away, but you're 4 feet away, relatively who's closer? Well, one has kilometers or something, and the other one has feet. But if I make z-scores, I can compare them because all the units go away. It's just a pure distance number. It just gives me relative distance, independent of units. So I don't care if I have kilometers and feet. If I make a z-score out of it, it's just a number. I can compare them then. If this is 1 and that's 2, then I'm closer to you relatively than I am from that 10. Relative to normal distances between towns, whatever. How are you doing on that? Is that? So the main thing to get from that is z-scores have no units. Yeah. A few more questions and we got this whole thing done. Let's see. On 17, define the percentile. I mean, if I asked you for the 12th percentile, you would go 12% of the way into the list. So to work it backwards, if I want to know what percentile is 54, I see how deep into the list 54 is. So I'd count how many places to get to 54 divided by the whole list size. Right? Get a percentage of how deep is it? And I think they have an example that goes through that, but that's pretty. Well, I thought they did. Blah 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 blah. Oh, here we go. Example 2, page 116. So to be more precise, you count up to this place, right? Because what's the percentile tell you? The percentage of the data that's below that data point. So you count how many data points there are below it, divided by how many total data points there are. So in this example, they refer to this data here. Okay, good. So 54, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of 24. So there you go. So 50th percentile, right? 12 divided by 24 is 50% of the way in. There's 50% of the data below it. Cool. How's that? Is that all right? Semi-decent? Again, both directions you go are based on going a certain percentage of the way into the list. A given percentile, I go that percentage of the way into the list. If I want to figure out what percentile a number is, I count how deep into the list it is. It's the same idea, both ways. All right. Oh, you have people glancing at the clock. All right. You can't possibly be that much time gone by yet. All right. Any other questions? There's still a few more there in that homework assignment. All right. So let's get back into chapter 4. And just to remind you guys what we did last time, we talked about types of probability. We talked about theoretical. We talked about empirical. And we talked about, I can't remember, I don't think we talked about subjective.
No, we did not.
This one doesn't enter too much, so I'm just going to discuss it right now, and it's not really going to come up too much. Subjective probability is if I asked you, what do you say the probability is of your getting stuck in an elevator in the next year? In fact, that's one of the problems in the homework. Some of you could base that on experience. Has anybody ever gotten stuck in an elevator? Okay. A few of us. In fact, everybody, that's kind of weird. You all have grouped yourselves together like survivors, just instinctively cluster together. Or were you all stuck in the same elevator and became friends? I don't know. So subjective is really more, you'd say to yourself, man, I got like a 10% chance of getting into class on time. You know, it's a very slim chance. What are you basing that on? You're basing that on your feelings and possibly a little bit of your understanding of traffic and the traffic lights and getting to school and finding a parking space. Do you see what I'm saying? Those kind of things. But it's still subjective. You're not doing any mathematical analysis on it. You're just saying, it's about a 10% chance I'm going to get to class on time today because I woke up late. Right? Or you say to yourself, man, I got about a 80% chance of acing this test, or because you feel pretty good, but there's always that chance maybe something goes wrong. Guys, so that's subjective probability. Obviously, it doesn't have too much of a place in statistical analysis, but this does include things like assigning a probability of rain. Very often, subjective probabilities can be based on experience, but they're not directly mathematically calculated like these two are. So yesterday we made a calculation. What's probably I get a head if I flip a coin? Half. Now, of course, not yesterday, but last time. You understand what the word yesterday means the last class. Empirically, what did we do to get the empirical probability of getting a head? Do you guys remember, what did we do? Theoretical means you don't do shit. You just think, okay, what could happen? Theoretically, what could happen? Empirical means observation, based on observation. So we actually flipped, I think, 16 of us flipped a coin, and the crazy thing is, exactly 8 people got a head. I can't remember, I think we were looking for it. And so empirically, we got probability of head to be 8 out of 16. You got it to be a half. Does it have to be that every time? If I ask you right now, 16 people, flip a coin, does it have to be 8?
Nope.
No. It could be what?
Yeah, it's 7 to 5.
Anything from 0 to freaking 18, right? Would we be a little bit freaked out if nobody flipped a head?
Yeah.
A little bit. Not like crazy, like, oh my God, but it'd still be like, well, that's kind of freaky, right? Sort of like hitting all green lights on the way to school, because it doesn't happen very often for those of us who drive. It does not happen very often, especially when you get really close. I'm gonna be there. No, I'm not. Okay, so does everybody understand the idea between these? This is the same thing like probability of rolling 2 on a die. Do I actually have to roll a die to do that? No. What would that probability be?
1 out of 6.
1 out of 6, and again, a normal die. If I wanted to get the empirical probability of getting a 2 on a die, what would I have to do?
Roll it.
I'd have to roll it many, many times. Okay. So what the hell does it mean then? What does this number actually mean? What does this number actually mean? Does it mean that if I roll a die 6 times, I will get 1, 2?
No.
Is that what it means?
On a huge scale, that's what will happen.
Exactly, because who remembers the name of that law?
The law of large numbers.
Law of large numbers connects these two. It's like a bridge between these two. The more I do this, the closer my number should get to this. So if I flip a coin 50 times and I get 20 heads, that's not freaky, that's 40%. But if I flip it 5,000 times, I should start getting closer to 50%. It's also called the law of averages, right? If you get a bunch of red lights, you should be getting green lights sometime soon. It's the law of averages. And of course, Murphy's law trumps that, but yeah.
Would it also mean that each time I toss the coin, I have a 1 in 2 chance of getting heads?
But what does that mean? Saying that doesn't really mean something. On a single time, if I flip a coin once, the 50% chance has very little to do physically with what's going on. You could say, well, it's got 2 sides. But what does 50% mean as far as what's going to happen? Not a damn thing. Right?
Yeah.
Each individual instance of something could happen or not. But what 50% in this case, for probably a head, or like we said earlier, last time, 90% chance you're going to survive a surgery. What does that really mean? That means over a lot of surgeries like this, 90% of the people have survived that have been in your situation, right? So again, like my little brother says, there's only 50-50, but that sucks. I don't want you to tell me I got a 50% chance of surviving some routine thing. Well, you will or you won't. Let's go under now. No. No. Okay. Maybe. So really, the question I could ask, or if I ask you, what does this mean? That means you could say, if I flip a coin 5,000 times, I'd expect, that's not a D, I'd expect to see 50% of 5,000, 2,500 heads. I'd expect to see that, or close to it, right? In fact, I was a little freaked out that we got exactly 8 heads, because there are more chances to get something else than 8. 8 is the highest probability, but there's more chances to get something else, because what's something else? 7, 6, 5, 9, 10, 11. There's more chances to do that. So it's a little bit weird that we got exactly 8. But obviously not impossible. Okay. So let me get a little more specific here. These are the big 3. This one we're not really going to talk about too much.
It's a strange question.
Cool.
Sort of missing the point. Is there a probability to expectations? Can you apply probability to people's expectations, and is it totally different?
We're getting into psychology now?
I guess.
Could be. It depends. But normally with statistics, we have what's called expected value. So you all know, what's the magic thing that happens related to insurance when you turn 25?
Your insurance rates go down.
Yeah, because somehow magically you wake up when you're 25 and you go, oh, that's how you drive. I remember hitting 25 and I paid a lot less money. And that's based on expected payouts for age groups, right? So to set premiums, they look at the probability of different age groups getting into an accident and the corresponding probability of how much money is going to have to be paid out. And once you hit that 25, that's just an arbitrary position they put for ages. You're now in this other group that has a lower probability of having these accidents, number of accidents, cost of accidents. You with me? So that's sort of not exactly your question.
Okay.
Expectations are hard to pin down,
Like
mathematically.
If you were to say, what is the probability that if asking someone to give you a random number between 1 and 10,
Oh, yeah.
there's a higher probability that they're going to say, there's a very high probability that they'll say something like 7.
And we did that. I showed you that data a while back. So that can be analyzed, because that can actually make observations. And that's, of course, a big part of statistics is used in psychology. You do a lot of random tests. You have people fill out surveys. You do weird things to them. You see what their reaction is. You do it a lot, law of large numbers, and you get a feel for what the theoretical probability is by doing experiments. So that's exactly where that goes to. Yeah.
Are you good enough at this to count cards?
No. I actually have honestly never tried, to tell you the truth.
Try.
If I have gone to a casino, which I've not done much,
Yeah.
because they're depressing to me, I will play card games, and I'm relatively good at poker, but not, obviously, if I was better, I'd be out there sitting next to Negriano and trying to win money off him. But it's so much more involved to it. You've got to have, more than just the math knowledge, because you don't very often see pure math people winning these poker tournaments because of the fact that it takes so much more than knowledge of statistics. Yeah, just like pool. I'm supposed to be really good at pool. My geometry students thought I'd be really good at pool. I'm okay, but nowhere near enough. I want to bet anybody anything to play some pool. I mean, there's a lot more than just knowing the angle. I know the angle, but the stick doesn't do what I want it to because I can't hold the damn thing correctly. The angle, I had the angle figured. Screw that shit. All right. Oh, let's see. Where was I going to go? Oh, we have a thing called sample space. It's got that magic name sample in it. And what this really represents is all the possible things that can happen in a given situation. So for a very simple example, flip a coin once. What could happen?
It could be heads, it could be tails.
It could be heads, it could be tails. There's your sample space. So sample space is just a collection of all the possible outcomes. You with me? What if I flip the coin twice? What could happen? It could be both heads,
Both tails.
both tails,
Be heads, tails.
heads, tails,
Or tails, heads.
or tails, heads. Good. Are these all equally likely?
Yeah.
Is each of these equally likely?
Yes.
Yes, assuming a fair coin, right? So these are all equally likely. So I could apply theoretical probability to this, and I really am trying not to make this sound harder than it really is, but I have to use the terminology. It's not difficult. What do you think the probability is that I'll get 2 tails if I flip a coin twice? 1 out of 4. Why is it that easy? Because these are all equally likely. You with me? So, since it's equally likely, then probability of tail, tail is 1 out of 4 because there's one of the things I'm looking for divided by 4 total things that could happen. Sweet. That's the basic definition of any probability is the number of things you're looking for divided by the number of things that could happen. That's really how all probabilities work. So I'm going to give you an example where it's not equally likely. And this is a classic problem. It's so classic, I'm getting a little bored of it, but too bad for me. Put 4 blue poker chips and 6 red poker chips in a bag. Pick one. What would the sample space look like? And don't overthink this.
Red or
The
blue?
sample space is everything that could possibly happen. I'm reaching in, I'm picking one poker chip. What could happen?
Get a red one.
Pick a blue one? Or you wouldn't say, you can pick a blue one, or a blue one, or a blue one. And you're like, you said that already, dude. You know? So the 4 and the 6, they don't come into play when you're making the sample space. Where do they come into play? When you're calculating probabilities. Which one's going to, of course, be more likely? The red poker chip, because there's more of them, right? So the sample space would just be red, blue. Cool? What's the probability of red, though? Is it 1/2?
No.
Hell no. What is the probability of red?
40%.
Yeah, because it's going to be 6 out of 10.
Oh, red.
Red, sorry, yeah.
Six blue.
I was doing the same thing you did. And what's probably a blue? That'll be 4 out of 10, 40%. And thankfully, all the probabilities add up to be 100%, which we know is true. Otherwise, I left something out. Cool. So this is the same thing. There's a problem in the book, and I'm hoping that nobody makes this mistake. Last semester, a lot of people did. We have a Republican and a Democrat, basically, coming up for election, right? You always have at least one other party that people know about and 52 other parties that I personally know about. And there's probably more than that, right? Nobody ever hears that, do you? All you hear right now is Obama versus we're not sure yet.
Yes.
That's it, right? But there's a lot more than that, trust me. Does that mean that there's a 50-50 chance that'll be a Republican president? There's a 50% chance it'll be a Republican? Of course not, because there's so many other factors going into this. In the last election, it was definitely less than 50% chance it was going to be a Republican just because of all these sentiments going into that election, right? We knew ahead of time that there was very little chance of McCain becoming the president. Still a chance, but definitely less than 50. So I can't just say there's 2 possible outcomes, therefore it's 50-50. All right, so I'll see if that comes out better. What if I pick 2? And let me make this right now with replacement.
Put it back in the bag.
But I put it back in before I pick another one. Right? This has become very important here very soon. What would my sample space look like?
Red, red, blue, blue, red, blue, blue.
Exactly. It's a lot like that head, head, tail, tail thing. Red, 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 blue, 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 red, blue, blue. You can do it, Joe. Again, are all these equally likely? Are they equally likely?
No.
No, hell no. Which one's the most likely?
Red, blue, red, blue. Yeah.
Red, red. Right? Almost sounds like red rum. Red, red is definitely most likely because, again, there's more red poker chips. You can't get away from that, right? Red, red would be the most likely thing to happen here. The least likely thing would be blue, blue. Good. So I can't say it's a 1/4 chance of this. In fact, right now we have no idea how to calculate this. We don't know. Okay. All right. So how are we doing so far? So, just to kind of build on this, the definition here, you have a sample space, and then you can define an event. And an event is a subset of the sample space. So for example, remember I flipped the coin twice. I had this. What's the probability to get exactly one head?
0.
No, come on now. Which means exactly one tail also.
Oh.
Right? So what's probably get exactly one head? So again, how do you put together a probability? What's definitely going to go on the bottom because these are all equally likely? 4. Out of those 4 cases, how many have exactly one head?
2.
That's all you have to do to put together a probability. On the bottom goes the total number of possibilities. On the top goes the number that match what I'm looking for. How many of these have exactly one head? Why not him? Because he has more than one freaking head. Right? He has 2, so I don't count him. He doesn't have any. He's got exactly 1. He's got exactly 1. So there's 2 out of 4 that match that. Cool. So this is an example of an event. Why? Because it was a subset. It was these 2, a subset of the whole sample space. You with me? So you can define an event any way you want to. You can define an event to be getting an odd number when you roll a die. Cool? That kind of thing. Any subset of what could happen. Okay. How are we doing so far? I don't want to get lost in the definitions here. The work is pretty straightforward. Let me make sure I don't miss any. Blah, blah, blah. Oh. By the way, I'm going to be talking a lot today. I'm going to lecture like crazy today, sort of continuing what I've been doing so far. Next time we're going to be basically group work for most of the time. We're going to be working on what I call a practice probability quiz. So I don't know how many of you realize the next graded thing. What's the next graded thing occurring? The double quiz. So I don't have the probability section on a test until the final exam, but I do have a quiz. I call it a double quiz because it counts twice as much as a normal quiz. So it'll be a little bit longer. So next time we'll have a practice probability quiz that we'll work together on in groups, and then you can see exactly the kind of questions they're going to ask. Okay. What's got to be true about probabilities? What's the least a probability can be? 0. What's the most a probability can be? And what does that notation mean? Well, that's what the idea means, but what's this notation mean? The probability of some event. I love it, right? So very often you'll see me use an X just like in algebra to represent some unknown, in this case, event. The event could be getting exactly one head. The event could be getting exactly 2 girls out of 3 children. That kind of thing. I like it. But it's obviously got to be below 1, at most 1, at least 0. What's the probability if you add them up? Add up all the probabilities, you of course have to get 1 or 100%. But we'll be using decimals mostly. And then finally, just to get a little ahead of this section, what's the probability of an event plus the probability of not that event? So for example, the probability it's going to rain today, I think it was 20%. I saw this morning, I already did. So. But the probability is, so then the probability it's not going to rain must be 80%. So of course, probability of an event plus its what's called complement. Very often given this notation, not A. Has to be what? What do they have to add up to be? 1 or 100%. Okay. So again, this is very simple ideas. You already know these ideas. It's just we're trying to formalize them just a little bit. So the probability of B was 0.076. What's the probability of not B?
Subtract that from 100.
Well, from
100%.
1.
1.
So what would that be?
9.2.
0.924. Like. Oh. All right, that's pretty straightforward, right? That's the complement. Known as complement. It just means the opposite of that event.
I was thinking 90.
Oh. Let's see. Cool. And that is section 4.2. How many of you guys don't know cards well at all? Like, for example, does anybody here not know how many suits there are in a deck of cards? I mean, at that level, I'm not saying we're going to suddenly play no holds, hold'em poker, or we're not going to play a gin rummy. No, but we all know how many suits are there in a deck of cards? 4. So cards have 4 suits. What are those suits?
Hearts, diamonds,
Hearts,
spades, clubs.
diamonds, spades, clovers, clubs. In my head, I was gonna make a joke about it. Sounds like Lucky Charms, and I thought that sounds stupid. Then I just kind of did it anyway. Hearts and diamonds. What do they have in common?
They're red.
They're red, and of course, spades and clubs are black. How many cards are in each suit? 13. There's, we'll call ace for right now, we'll call it low as a 1. It could be a high. Up through 10, 11 is jack, 12 is queen, 13 is king. And that's true for all of them. So there are 13 cards in each, right? So how many total cards are there?
52.
52. Of course, that's an important number. Second.
Plus 2 jokers.
Oh yeah, take the jokers out. That's an important number because when I want to create a probability, that's the number that's got to go on the bottom, right? Because it's the total number of things that could happen. So it sounds like nobody, at least if you're not familiar with cards, you don't want to speak up about it. It's nothing to be ashamed of or anything, but it just makes it easy for having something to pull out of some events. So if I pick one card, from a deck that has no jokers in it, right, regular deck, pick one card, what's the probability that I pick a king? So what's definitely going to go on the bottom? Don't reduce it yet. 52. Out of 52 cards, how many chances do I have to get a king? The biggest mistake I see on this kind of problem is somebody tells me the answer is 1 out of 4. What mistake do you think they made? They tell me the answer to this is 1 out of 4. They say to themselves, oh, there's 4 kings and I want to get one of them. But you're not just choosing from 4 cards, you're choosing from 52. And you have 4 chances to get that kind of card. Do you see the difference? Bless you. So what does that reduce to?
13.
So a lot of times when probabilities reduce, that means there's another way to look at it. For every 13 cards, how many kings are there? There's 1 king for every 13 cards. So there's another way to kind of look at the probability. Oh no, for every deck, there's 4 kings, but for every suit, there's 1. Okay, cool. All right. So here's where things get more interesting. What's the probability I get a king or an 8? So I'm going to pick a card from a deck of cards. I can get a king or an 8 and win money.
Yep.
So again, it's the same idea, and this is what I really want to stress. No matter what level of probability you're working with, and we're going to learn a lot of different levels, they all are basically set up the same way. On the bottom goes the total number of things that could happen. On the top goes the number of things that match what you're looking for. 4 things match this, 4 things match that, 8 total things. 8 distinct cards, right? And what does that reduce to?
2 13s.
2 out of 13, which again makes sense. There's 2 of what I'm looking for every suit, every 13 cards. So what's different then with this? First off, how many face cards are there? How many cards have a face on them? Careful. Ace doesn't have a face. 12, right? Jack, queen, king for each suit times 4 is 12. Are we all cool with that? So there are 12 face cards. How many kings are there? If I do this, am I okay?
No.
Why not?
King is a face card counted twice.
King is a face card. Yeah, I've counted it twice. I've counted every single king twice. So if I do add 4 to 12, I better subtract any card that's both. And again, why would I do that? Because I'm not being honest if I just add them together, because I'm adding 4 of them twice. Right? It's like saying I need 5 people to help me. All the men here stand up. All the men stand up and then say, okay, all the people that own a Lexus stand up. And of course, some of the men own a Lexus. They're going to be already, I'm going to think I'm getting more and more people, but I'm not. I'm have a few people that match both of these already. So I can't count them all. I'd have to subtract off the 4 that I double counted. Yes, sir.
Is this how you want us to show our work?
Not necessarily.
Okay.
When you're counting things, you could be much smarter about it and say, I've got 4 kings. I got 4 kings plus 8 other face cards I haven't counted yet, right? And what did I do? Not 8 other face cards. Yeah, 8 other. Okay, good. That's right. 12 out of 52 then. And that's the same thing we get over here, 12 out of 52. So I want to be really careful. This is where probability formulas very often make it harder, believe it or not. And I'm going to totally confess to this. They often make it seem harder due to a problem than it really is. It'd be much smarter for me to say 4 kings plus, oh, there's 8 other face cards. Instead of doing 4 plus 12, oh yeah, minus the 4 that are both. You know, the formula is going to look like that because it has to be more general. But I could do this specifically. You'd be smarter about it, yeah.
Will you accept a king as a face card and there are 12 face cards? So just,
Oh yeah, so
I thought you
exactly.
told
So
me.
12 already includes it. Yeah, good. I like it. As long as you kind of explain it to me. Yeah. What about this here? Let me do one more like that. Jack or a club. So again, how many jacks are there?
4.
4. How many clubs are there?
13.
13. But of course, if I do that, what mistake have I made?
One of the jacks is a club.
Yeah, one of the jacks is a club, so I counted it twice. Cool. Okay. So I have to subtract it off. Or again, I could be smart about it and say 4 jacks plus 12 other clubs I haven't counted yet. Because when I count the 4 jacks, isn't there a club in there already? So how many clubs have I not counted yet? 12 other ones. They both end up at 16 out of 52. So what I'm trying to get to is the general formula for OR. That's the key word here is OR. The general formula for OR is the probability of one of them plus the probability of the other one minus any that are both. Minus any that are A and B. Like up here, I had to subtract a 1, and what's that one card? It's a jack and a club. Or in English, the jack of clubs. In math, it's jack and club. That's, if I remember correctly, basically your first official probability formula. And that, of course, amazingly enough, is called the addition rule. So OR is basically add. And the reason I don't say it is add is because sometimes you have to take off something if you double counted anybody. Okay. Maybe. So continuing this idea, I'm going to I always do chapter 4 out of order. So don't worry, we're going to do it all today anyway. Yay, Jeff. I like this question because it involves, for one thing, fake money, not real money, because I can't give any of my money away. Well, much of it to do that. But let's say I had a deck of cards and you could pick one card and you could put money, I'll look at it, you don't look at it. Okay? And you could put money down on what card it is. Right? And then I allow you to ask one question to try to figure out if you want to stay with that card or not. So let's say you do pick a card and you have this strong suspicion, I'm looking at it, you think it's a queen. Right? You're pretty sure it's going to be a queen. In fact, let's be more specific. The Queen of Hearts. You just know, because that song was playing on the radio that morning. There was a song. Do you know the song? No. I'm not going to sing it. Ace of Spades are. Got the wrong decade. So the Queen of Hearts, we think that's what it is. So what's the probability that you're right? If you're going to put money on the Queen of Hearts, what's the probability that you're right?
1 out of 52.
I like it. So what's a good question you can ask to increase your probability?
Is it black?
Yeah, you could ask a question like, is it black? Is it red? You know, that kind of question. So if I say, no, it's not black. So you could ask, so one question I could ask is it black? And you understand the idea is, if I say, yes, it is, you're obviously going to change your guess, right? You say, okay, I don't want to put money on the Queen of Hearts. It obviously can't be that. I'm going to put money on something else. But let me say, my answer is no. So could anybody figure out what's my probability now? Will my probability change?
Yes.
Should it be more or less likely for this to be true?
A lot more likely.
More likely. What will it be now? So what's the probability? It's the Queen of Hearts. And here's the magic word here. Given that it's red. Because it said no, it's not black.
1 out of 26.
So what should be on the bottom now? On the bottom is all the things it could be. And what's the only thing I know for sure about this card?
It's red.
I know it's red. So how many red cards are there?
26.
Given red, that means there could only be 26 things it could be. So the only time, this sounds like a note, the only time the bottom isn't the total of everything is when you're given information. Then you can cut some things out. With me? So what's happened to our probability now? What's on the top? Yeah, there's still one card, but now out of 26, I've increased my probability by a factor of 2. Still not the best odds in the world, but a lot better than most gain some chance. Yeah, we doing so far. What's another question I could have asked besides, is it black? Is it a heart? Okay.
Yes.
I like that one.
What suit is it?
Hold on, let me do one at a time. Question 2, is it a heart? And I say yes. You guys take a second, don't say anything out loud. What would my new probability of Queen of Heart be? Don't say anything out loud yet. So again, these are separate. You only get to ask one question. You could have asked this, and that would have happened. Or we could ask that, what would happen then? What's going to be on the bottom now? 13. Because you know it's a heart. How many hearts are there? 13. Out of those 13 cards, how many match what I'm looking for? 1. Cool. How you doing so far? You guys see how this is called conditional probability, which makes sense. On the condition of something else, this is what the probability becomes. And the key word is given. Okay. Sort of. All right. So let me try to put together what the formula is for this from what we've been doing. So in notation, we probably have A given B. That's not a division line. This kind of sucks for choice for symbol. Let me make sure I remember this book does that. I think it does. Yes, it does. This means given. This does not mean A divided by B. It's probably A given B. So tell me, what event do I know happened in this case? Which event, A or B, do I know happened? Read it. Probability of A given B. So which one happened? B. Yeah, I kind of led you there. But that's how you read it. That's how you read this in English. What's the probability of A? I have no idea what the hell probability of A is. Given that B happened, okay, cool, B happened. So let me give you an example I like a lot. Oh, good. And this is where people get in trouble for all the wrong reasons. Let me just say this example and see what you guys think. And this is not too controversial, so I'm not going to get in too much trouble. If you see somebody drive up and somebody's like, there's somebody coming, what's the chances that that person is a man or a woman? What would you say? It's probably is a man. What's probably that dude is that person is a man. That dude is a man. Kind of good. It's probably that person is a man. I'd have to say 50% roughly. Cool? You with me so far? That's pretty simple. But then the guy says, the person just got off a Harley, a motorcycle. That person just got off a motorcycle. Is the probability that's a man, has it changed now?
Yeah.
And in fact, it's done what? Is it still 50%? No. It's higher or lower? Higher. So again, this is where you get into, if you talk about controversial subjects, you get in trouble, even though you're just talking about the probabilities. People very often get confused. They think you're saying this. No, I'm saying the probability has gone down or gone up. I'm not saying that you are definitely this way. And this happens a lot in politics because people are very confused about statistics, so they take it to be a true statement. You all agree that the probability, if I see a person get off a motorcycle, the probability of a man is definitely going to be a lot higher than 50%. It's not 100% because there are women who ride motorcycles, of course, but a lot fewer. So that's a nice, I can kind of see a person get off a motorcycle. I like that. That's an example of conditional probability in the real world. And we do this all the time. We drive a certain time of day. Do you always go the same route? If you want to go from one point to another at 9 a.m. versus 5 p.m. in San Diego? So there's a conditional probability. The probability I'll get there in a decent amount of time in the morning is better here, but in the afternoon it's better this way, right? And so we apply conditional probabilities all the time. We're not calculating math, we're just applying the idea. Yeah.
That conditional probability can you also apply that you make it even stronger if you say, okay, if they're arriving here at a college campus, then it's going to be
Oh, sure, of
higher
course.
than this.
Yeah, you could keep extending this list, given it's red, given it's this, given it's that, given it's that, and that just really narrows down your possible pool, right? You guys with me? Given that I got off a Harley, oh, and they're wearing this, and they're 6'5" tall. Oh, well, shit, now the problem is the man is becoming really high, right? Okay.
Turns out to be a woman.
Yeah, and then it's a woman. You're like, wow. But see, that's the mistake people make. They take specific examples. You see this in politics a lot. I love it when they have a speech and they talk to. I got a person in the audience today, and she went through the same thing, and she's fine now. And you're like, you can't prove a damn thing with a specific example. You can't say, well, it's a woman. Well, damn. Everybody rides a freaking motorcycle as a woman now. That we know is stupid. But that kind of thing happens so often in other situations. Oh, I saw this. That must be what it is for everything else. No, that's stupid, right? We got to keep in mind the probabilities. That will happen. It could have been a woman at 6'5", wearing big spikes and coming over. And yeah, it could be a woman. Why not? But it's probably a man. It's most likely a man if I don't see who it is yet. Okay. So how does this probability get set up? Why do we keep putting? Well, I kind of messed up how I wanted to do this. It's too bad for me. What is definitely on the bottom here? What definitely goes on the bottom? In general now. I mean, in general. Probability A given B. Why do we put 13 on the bottom here? Because it was given what? Given that it was a heart, right? Why did we put 26 here? It was given that it was red. Cool? So what definitely goes on the bottom?
2.
Do you keep saying 2? No, don't say 2. Because here's 13, for example. So it can't be 2. The bottom has got to be related to the given thing, right? And in fact, in general, what goes to the bottom is the probability of the given. Okay. Now, I set this problem up differently than I have in the past, and I just realized it really doesn't help me. I can't see what the top is supposed to be in general, because it's always 1 in my example here, right? But let me give you a little different setup. Probability of a king is what? Probably pick a king would be, there's 4 kings out of 52 cards. What's probably is a king given, it's a club.
1 out of 52.
Careful. What goes on the bottom?
13.
13. And what goes on the top? Not 4. 1. Why'd you say 1? Why didn't you put 4? There's 4 kings. Because there's only 1 king that's also a club. So in symbols, what's the top thing then? It's probability of king and club. The top has got to be both of these. You with me? Given that the person rode up on a motorcycle, the people on the top have to all ride motorcycles because I'm throwing out all the people that don't. Given that it's a club, the top has to be a club. But it also has to be a king to match what I'm looking for. You guys with me here? Okay, so I've thrown out all the other suits. How many things match what I'm looking for? Anything that's this and this. So the formula is probability of a given is and over given. One way to remember. You don't have to remember it because you can put it on a formula sheet, but there's a little saying. Now I'm okay with glancing at the clock. It's okay.